Today we're going to go over just a little review of orbitals and sublevels and go over a couple of examples of figuring out electron configurations and using the periodic table to make that happen. So at this point you should be pretty familiar with orbitals and sublevels and also with filling them with electrons because of the activity we did in class. But I just want to review the shapes one more time. So if you remember from the short video you watched the other night, the s orbital is a sphere shape. Each energy level has an s orbital, and all of them hold 2 electrons. And as you go up in energy, the s orbitals get bigger and bigger. So the 1s is the smallest, 2s is a little bit bigger, 3s is bigger, and so on. And then the p orbitals are sort of these dumbbell shapes. One along the x-axis, one along the y-axis, and one along the z-axis. And each of those different sublevels holds 2 electrons, so the p's all together hold 6 because there are 3 of them and they each hold 2. Okay, so now we're going to go into some examples of electron configurations. When we did the boarding house model in class, we talked about rules for filling the beds, or in our case, filling orbitals. And we discussed that you would never go to the second floor before the first floor is full, or the third floor until the second floor is full, and so on. But I just want to tell you about a little bit of an exception when you get to higher energy levels, and a diagram that can help you remember the order that the orbitals are going to fill. So for the first couple levels, it's just like we discussed. You fill 1s, and then you fill 2s, and then 2p, and then 3s, and then 3p. But when you get to 3p, or after 3p, things get a little bit different. It turns out that it takes less energy to fill a 4s orbital than it does to put electrons into the 3d. And so when we fill the orbitals, the 3p, after that one is full, you add electrons to the 4s. And then once the 4s has 2 electrons in it, then you go back and add electrons to the 3d. Okay, so to remember this order, I'm going to show you a little bit later how to remember it with the periodic table, but you can also write out the energy levels like this, from 1s, 2s, 2p, 3s, 3p, 3d, and so on, which you should be able to remember because you add one new type of sublevel for each energy level as you go down. And then if you draw diagonal arrows, that tells you the order of filling. So as you can see, the 1s to 2s to 2p to 3s to 3p is the same order, but then your diagonal arrow goes from 3p down to 4s rather than going to 3d. So it's not until after you do 4s that you go back and do 3d, and then 4p, and then 5s before you do 4d. Okay? And we're never really going to get to filling f orbitals in this class, so you don't really need to worry about those. The main exception you need to remember is that 3d doesn't get any electrons until after the 4s is full. So let's go over a couple of examples. I'm going to go over how to do the orbital diagram and the electron configuration, which we've already done in class with the boarding house model, and then I'll go over what the abbreviated configuration is and how you would write it. Okay, so the first one we're going to do is nitrogen, and if we look at the periodic table, nitrogen has 7 electrons. Okay, so that means we're going to start with the 1s. We're going to put 2 in there and fill that up before we move to the second energy level. Then we're going to add 2 to the 2s, fill that up before we move to the 2p. And then we have 3 electrons left, so we're going to put 1 in each of the p orbitals before we put 2 in any of them. Okay, so our electron configuration is going to be 1s2, 2s2, 2p3. Okay, now for the abbreviated configuration, or sometimes I'll call it the noble gas configuration, that's a configuration that only shows the electrons in the outermost energy level, or the highest energy level. So in this example, the 1s is already completely full. So we're only going to show the electrons that are in the 2 sublevel. All right, so in order to represent those that are in the shells that are the inner shells that are already full, we use the noble gas that has that number of electrons. So there's, right, for nitrogen we only have the 1 full, and so the noble gas that has a full 1 energy level is helium. So we're going to do helium in brackets. And then the remainder of the electron configuration we'll write out because that's the second energy level that's not yet full. So our abbreviated configuration for nitrogen is going to be helium, and you always want to put it in these brackets, 2s2, 2p3. Now we're going to do one more example, and we're going to use magnesium, which has slightly more electrons. And if we look at the periodic table, magnesium has 12 electrons. So we're going to start with the 1s, add 2 electrons there, add 2 to the 2s, and then add 6 total to the 2p. And then for the 3s, we've now used 2, 4, 6, 8, 10 electrons, which means we have 2 more left, and so both of those are going to go in the 3s. So now our electron configuration is 1s2, 2s2, 2p6, 3s2. Okay, so now let's do the noble gas configuration. So in this case, because magnesium has electrons in the 3 energy level, that means that the 1 and the 2 are completely full. And so we're going to condense all of those electrons into the abbreviated configuration. So we need to find the noble gas that has a full 1 and 2 level. And so that is 10 electrons total, and that would be neon, which is the second noble gas in the group. And now the last thing we have left to do is just write the electrons that are the outermost electrons, which are just the 3s2. So we'll just add 3s2, and then neon 3s2 would be the abbreviated electron configuration for magnesium. Now I'm going to go over some examples that use the structure of the periodic table to make it easier to find electron configurations. So this example uses chlorine as an example. So the first thing that you want to do is find chlorine on the periodic table. Now we want to start in the upper left-hand corner with 1s and write all of the filled sublevels in order going across each period. So for chlorine, that would be 1s, which holds 2, then 2s, which holds 2, and then 2p, which holds 6. And then we go to the next row or period, and then 3s holds 2, and then we're into 3p, but chlorine doesn't make it all the way to the end of 3p. So we write down 3p, and then we count over 1, 2, 3, 4, and then chlorine is number 5. Okay, so that would be the number that becomes our superscript. Now we're going to go through the same process for selenium, and you'll see how much easier it is to use this method than if we were to be using the simple counting method we've been. Okay, so first we have to locate selenium on the periodic table, and it's right here. And then we can start our count over from the top left. So we do the 1s first, and there's 2 there, then 2s, then 2p, 6, then 3s2, then 3p6, now 4s2, and this is where the periodic table helps you remember the filling order if you can't remember that table. Okay, and then we go over all of the 3D, so that's 3D10, and if you can't remember how many are in there, you can just count the blocks. And then we get to 4p, and selenium doesn't make it all the way to the end of 4p, right, but we have 1, 2, 3, 4, and that would be our superscript for 4p. And with a element that has this many electrons, it's always a good idea to go back and add up your superscripts and make sure they add up to the number of electrons. So selenium has 34 electrons, and if we do 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 4 is 34, and that's how many electrons selenium has. So we're good, right? And then this method also makes it really easy to find the abbreviated electron configuration. So all you need to do is find your element, which we already did, and then move up one period or one row and go to the end and find that noble gas. Okay, so in this case, that noble gas is argon, which is right here. Okay, and that represents the core electrons for this element. So we can represent all of this based on just the argon in brackets. And then what remains, we write after the little argon symbol, and that's our abbreviated configuration. So our abbreviated configuration for selenium is argon 4s2 3d10 4p4. So that concludes our lesson on electron configurations and orbital diagrams. And we're going to build on this and practice this more in class. And in the next section or two, trying to understand why we care about what the electron configuration is and what can it tell us about the properties of a particular element.